Have you ever heard about bubble generation, or just like bubble behind me? Of course, you have seen that in your daily life. But did you ever think this small bubble were very important, especially in science application because of its performance? And also, did you know about microfluidic device like this? Okay, in order to perform this quality bubble generation that were used in science application, scientists or professional workers were used in this device to get bubble formation. Based on statement from Shelley and Anna, microbubbles are widely used in many fields such as biology, chemical industry, and medical. But for microfluidic device, based on article from Bubbles and Forms in Microfluidics, they say that microfluidic device can allow for high throughput production of bubbles with very well controlled size and generation frequency. So this device is very useful device in order to perform bubble. In order to get know more about what I'm doing in my project FIP, come, I will show you. So these are my project, which is CFD of bubble generation in co-flowing microfluidic device. First of all, I want to thank to my supervisor, Dr. Ali Nadia Abdul Latif, for always guide me until I complete my project. And also I want to thank to my panel, Dr. Al Hassan Salami Tijani and Madam Rose Nadia for watching my presentation. As I mentioned before this, microfluidic is the device that used to form bubble generation. This is because this device can control fluid flow in microscale channel and form bubble formation. Two figure above shows the example of the microfluidic device. This device mostly we can find in biology and chemical application. In my FIP project, I'm using multi-phase flow, which is flow that contain two phases that can introduce as continuous and disperse phase. In order to form bubble in this flow, I'm using immiscible flow, which that flow that not be mixed together. So I'm using oil that used in continuous phase and water that used in disperse phase. This microfluidic device has many type of geometry design, such as T-junction, cross-flowing geometry. But in this project, co-flowing geometry will be used to form the bubble. This co-flowing geometry has two channels, which is outer and inner channel. This outer channel will use to flow continuous phase, and inner channel is used to flow disperse phase. Microfluidic system in this project is used to produce bubble performance in order to analyze the size of bubble, the volume bubble, and the frequency. Parameter is important as it can give the result of bubble performance. Viscosity, velocity, also density of the fluid will be used in this project as the parameter. As this microfluidic device were used in many science applications, the functionalities of microfluidic material still lacking in order to obtain another approach or outcomes of the result because they're still using hands-on method. So, in order to get this approach, this can be solved using CFD simulation by using co-flowing geometry in this project. Many studies will be done to analyze bubble formation, but the effect of continuous phase and disperse phase viscosity will still lack in the study. So, the objective of this project is to develop CFD model of multi-phase flow in microfluidic device with co-flowing geometry design to investigate the effects viscosity of continuous phase on the size, volume, and frequency of the bubble formation. In order to make the simulation in this project, the methodology need to be great to know the step of the project. So, the criteria of this project model the use with the multi-phase flow, which contain immiscible phase that use oil as continuous phase and water as disperse phase. Type of geometry were co-flowing geometry, which can hold for two fluid flow in one channel but been divided into two channels, outer and inner. Flow that been used with laminar flow as we want to get a smooth flow of bubble formation. And the method that been used is VOF, which is volume of fluid. This method is used because it has surface tracking technique that can be used in fluid flow, and also it is suitable method to use in analyze the two immiscible fluid or more. In this slide is the flow chart of the project. As the first step will determine the parameter. The viscosity is the main parameter because this viscosity is used to determine the bubble formation. The viscosity of the continuous phase, which is oil fluid, is the main character. Another parameter that been involved was the velocity of the oil and water. After that, the previous study will be used in order to design the two-dimensional channel of co-flowing geometry using CFD and Fluent software. Next, we'll do a meshing part in the 2D co-flowing design. This meshing part will use to give more accurate of bubble formation. As with many types of meshing, the most accurate and mostly used in CFD simulation were quadrilateral mesh that been chosen in ANSYS Fluent. After that, the boundary condition is important to apply in this model as we use no slip condition. BOF method also need to apply because it is important method to give the result in bubble formation. After all the criteria has been set up, the model of co-flowing need to be run to get the result data of bubble formation in its size, volume, and also its frequency. These are the values that been set up in this model parameter. All these values will be get from the previous study from Taufik Chakafi in article of computational study of droplet breakup in drop channel configuration using volume of fluid method, and this used as the validation result once the simulation will be done to do next simulation. The capillary number has been used for the dispersed phase and also the Reynolds number to get whether the result is in range or not based on the formula given. And after the simulation done, capillary number and Reynolds number will get in range. These are the co-flowing geometry that has been modeled. This co-flowing contains two channels in it, which is for continuous phase for outlet channel and dispersed phase for inlet channel. On the figure below shows the co-flowing model in meshing section in ANSYS Fluent. The result that been get will be divided into four results, which is the formation of bubble, effect of viscosity of the continuous phase in bubble size, effect of viscosity of the continuous phase in volume of dispersed phase, and also the effect of viscosity of the continuous phase in the frequency. In this project, the validation of the model will be used to get the result in range. From my project, the bubble size that I've been get were in range as the previous study, also for the frequency and the volume of the bubble. The viscosity is the main parameter, so that my project is valid and accepted to the next value for this simulation. The validation value that been taken from the previous study were the viscosity of the oil in continuous phase, which is 0.0083, 3.31, and 8.29. The next slide, the first result that been get, which is formation of bubble. The first things that been identified were the Reynolds number and capillary number. As this simulation will be used in investigating dispersed phase viscosity, which 0.00103, so the Reynolds number is been implemented using a parameter from dispersed phase. From the result, it can be said that Reynolds number were categorized in laminar range because it's lower than 2300. The capillary number that has been get also in range, which is below 0.005, and this bubble formation will be put in dripping mode, where the bubble is pinched off and perform ellipsoid shape. In this analysis, when the viscosity increase, it will increase the capillary number. After the Reynolds number and capillary number will be kept in range, next is to analyze the stage formation of the bubble. In this bubble formation, it undergoes two stages, which is expansion of the bubble and necking of the bubble. The stage will be get using the viscosity of oil at 8.29. For the stage 1, based on the video shows that the thread of the bubble become expand. This is because when the dispersed phase, which is water thrust, will appear at the surface tension of water and oil interface. At this stage, the tip of bubble become ellipsoid shape. For the next stage, with the necking of the bubble. Based on the video above, it shows that the bubble begin necking and the tip appears at the thread, and this is because the influence of the large oil pulling force that leads the width of the neck becomes smaller, and then the force interface of the channel will break the neck of the thread and form the bubble. Video below shows the bubble formation within time with using the viscosity of the oil in continuous phase at 0.0083 and 8.29, which very low viscosity of oil and very high viscosity of oil. Based on this video, it can be compared that the low in viscosity in continuous phase can produce bubble in short time than using high viscosity. This is because high viscosity in continuous phase has high resistance, which is require more friction to flow within the wall, and flow becomes slower and need time to meet the fluid from the dispersed phase to form bubble. Based on figure shows that 6 viscosity of the oil that been used to form bubble generation and shows that time need to form bubble. Next result were the effect of the viscosity in bubble size. For the first step, the measurement of the bubble need to be taken from two different directions, which is x in y direction. Based on the figure, it can be shown that in x direction, it requires higher radius length than in y direction. This is because of the stretch lengthwise due to the impact of the liquid flow in horizontal direction and also the action of the surface tension, so that the bubble increase and grows into ellipsoid shape. Based on the table shows that the value that been used for the validation to be compared with previous study. In this part, the range of the bubble size will be determined using 5 bubbles. From the first to 5th bubble, the size will increase in both directions. This is because the pressure on the liquid surface varies with depth. So, when the length channel will increase, the depth increase and pressure also increase. That causes the bubble increase in its size and volume. After the value of the validation will be get in range with the previous study, the next value viscosity of oil in continuous phase will be used, which is 1.5, 2.5 and 5. Based on the table from both directions below shows that when the viscosity of the continuous phase is increased, the size of the bubble decrease. This is because when the viscosity of oil in continuous phase increase, the force that flow the dispersed phase, which is water, also increase because they need to flow along the oil viscosity, and that will allow the surface tension force to break up faster, and drag force that act on the bubble also become higher, so that the force balance will reach faster and give small size of bubble. This slide shows that the graph of mean average bubble size in both directions. It concludes that when the viscosity of the continuous phase will increase, the bubble size will decrease. The next result would the effect of the viscosity of continuous phase in volume fraction of dispersed phase. In this part, the volume fraction will be set from 0 to 1, and based on the graph, the volume will get in range. From the graph below shows that which from the mean volume fraction, it shows when the viscosity of the continuous phase increase, the volume of the bubble size that form from the dispersed phase would decrease. This is because when the viscosity in continuous phase will increase, the viscous shear that acting at fluid interface also become bigger and then produce small bubble, leading to have small volume. In this slide shows that the effect of the viscosity of continuous phase in frequency of bubble formation. Based on the graph shows that when the viscosity is increased, the frequency of the bubble formation also increase. This is because when the high viscosity been applied in the continuous phase, the shear force among the continuous and dispersed phase will high, and that will cut the thread faster and affect the bubble size and the frequency. At the viscosity of 8.29, will achieve high frequency, which is 950 Hz. After that, the effect of increasing viscosity in continuous phase also make the thread of the bubble will shed off faster, and it leads to the increasing of the frequency. This slide will show the contour of viscosity from viscosity 0.0083 to 8.29. As the conclusion that can be made, the viscosity is one of the important parameters that give the result of bubble formation, and it also can use to obtain new approach in science application. And volume of fluid method is useful way to form bubble in microfluidic device. Thank you. That's all from me, and I hope that you will understand regarding my project. Thank you and Assalamualaikum.